Hello, this is the aolithium LiFePO4 12 volt 100 amp hour lithium battery with Bluetooth 5. So what can you do with Bluetooth? Well, it means there's an app on which you can monitor state of charge, voltage, current, temperature, power, and all sorts of other stuff. I'll take the tablet indoors and we'll have a closer look. So this app is in the Google Play Store. It's very easy to find. Just look up aolithium. So yes, it shows state of charge, currently 85%, because I have been charging this battery. It shows the state of the charge MOSFETs, the discharge MOSFETs, the balancing circuitry, and the battery protection. It also shows the battery voltage, the current, the battery is just sitting here, so there's no current going either in or out, temperature of the battery, power, and there's more stuff, number of cycles, charge and discharge. I haven't actually fully discharged it yet. The average voltage of the 4 cells, there are 4 cells in series, the nominal capacity, once you've done, I think, 2 full charge and discharge cycles, this will update to give you the actual battery capacity, and what they call residual capacity, which actually is state of charge, 85%. Now, at first glance, I thought, oh, that's a shame, it doesn't show the individual cell voltages, but it kind of does, or at least it shows 2 of them, and here they are. They look a bit strange at the moment because we're in a very high resolution state. So this is the voltage of the highest voltage cell, and the blue line is the voltage of the lowest voltage cell. The yellow line, which you can barely see, is current, and the current scale is over here. Interestingly, this thing moves to the left, so the actual voltage now is the rightmost position on these 2 lines, but the scale is over on the left, which is a little bit of a shame. Here we've got the current again in yellow. It's barely visible. The green line, I think, is state of charge, and on the final screen or graph, we've got temperature of the battery. So if you start charging it, the blue line will rise up. These are auto scaling, so they all look a bit strange at the moment because they're showing you the resolution of the A to D converters. Also, current's on there. It's on the 0 line. It's in yellow. It's not very easy to see. And the final page of information is this, it's parameter. Now all this is a set of static voltage parameters which show you cell overcharge voltage, which is 3.65 volts, the overcharge voltage release, 3.5 volts, cell over discharge protection at 2.5 volts, the cell over discharge voltage release, which is when it comes back up to 3 volts. And then really you've got the same 4 parameters for the battery as a whole. Charge to 14.6 volts, overcharge release happens at 14 volts. Over discharge means that the MOSFETs switch off at 10 volts, and over discharge release is when the battery recovers to 12 volts, the MOSFETs switch back on. And then the only other things you've got are the Bluetooth searching facility and a My page, which is just an aolithium splash page. Now, just some stuff from the supplied manual. This thing here, 4S, doesn't specifically refer to the fact that there are 4 LiFePO4 cells in series in here. What it actually means is that you can put 4 of these batteries in series to build a 50 volt system, and you can see from this table, at first glance it looks like all the numbers in this table are the same. I mean, you can see the weight and the dimensions here. But down here is an indication of how that increase in MOSFET voltage has affected these 2 units. The previous version, where you could put 2 of these batteries in series, you could overcurrent it to 200 amps for less than 3 minutes. The 4S version, you can overcurrent it to 200 amps for less than 10 seconds. So they've upgraded the MOSFET voltage capability, and it's had an impact on the current handling. And some details on the charging: charge to 14.6 volts, keep the charge current below 50 amps. The maximum charge current is 100 amps. maximum discharge current is also 100 amps, but with this capability for 200 amps for a short burst. And also from the manual, the 12 volt 100 amp hour version of the battery, you could stack 2 in series, 4 in parallel, or this series parallel array. But this 4S version of the battery, you can put 4 in series or 4 in parallel, or a series parallel array of 4 in each dimension. So let's get this battery charging. Now I've made up some little M8, these are M8 bolts, M8 lugs to a 4mm banana jack, so I'll just put those under the screws. So this is really simple. I've got a solar panel here, might even get the sun to come out for a few minutes, and it's simply plugged into the positive and negative on the battery, and you can see here that we've got a current of 2.2 amps. The voltage is 13.36, 28 watts of power. The sun's not out yet. And if I switch over to the graphs page, we should now see the cell voltages start to go up. So we'll give it a little bit of time to build up some history. Right, just a little blast of sunshine, and we're seeing, well, we were seeing 4 amps. Did that push the voltage up? Yes, to 13.4 volts. Yeah, I think we might have a more sustained blast of sunshine in a moment. And there's 6.3 amps. Briefly, voltage has pushed up, and if we now switch over to the graphing page, you can see that the lines have pushed right up. Now, as I say, the numbers on this side are not for voltage, they are actually for current, which is the yellow line. So you have to track across to the other side and pick the voltage up from here. So it's about 3.35 or thereabouts. These charts update every minute, and I think the chart stores, I think it's 1 hour and 40 minutes across there. Well, there's no sun now, so I've set up a charging setup with a power bank and this current and voltage regulated power supply, and I'm monitoring on the app. I've got 5 amps of current going in, 66 watts. Does that tie up with this? Yeah, 4.99 amps, 69 watts it says on here. I'm having to use a buck boost converter because I've got 12 volts going in. In fact, I've got 12.4 volts going in and 13.8 volts coming out, so it's doing a little bit of boosting at the moment. It's a little easier to see what's going on inside, so I'm just near the setup, which is out there on the bench. So the 5 amps is going into the battery, voltage is 13.5, power is 66 watts. The average voltage of all 4 cells is 3.375 volts, and the battery is at 86% state of charge. Okay, let's switch over to the history page so that we can look at the graphs, and now you can see how the red and the blue lines, which are the highest cell voltage and lowest cell voltage respectively, the average cell voltage being the green line, although they're all pretty close to each other, and the current, you can just see there that it's peaked at 5 amps. The earlier part of the curve here is when I had the solar panel on there. I'll just check that the power supply is not getting hot. No, it's absolutely fine. The little fan on the back of the heatsink there is running. Now if I switch to the history page, you can see here what I mean about measuring the upper cell, or the cell with the highest voltage and the cell with the lowest voltage. This scale here is actually the current. You can see, well, you may be able to see the yellow line is by the 5, but the voltages for these two lines are actually over here, and this scale keeps changing to some quite crazy numbers. So at the moment it's 3.37, 3.38. So the cell voltages are very close to each other, somewhere between 3.37 and 3.38. 8, maybe 3.375. When you're charging, you get an estimated charge time here, which is derived from these parameters. When you're discharging, of course, you get an estimated discharge time. This one's an interesting thing here. You've got the charge switch is open. Now, open means enabled. But of course, in switch terminology, open means not connected, but this means connected. So an open charge switch means an enabled charge switch. There's also an open discharge switch. The balance state is closed. That will open when the battery starts to balance the highest voltage cell. And the protection state is closed, meaning it's disabled, so the battery is not having to protect itself. Now look how flat the voltage curve is of the highest and lowest cells. They're almost completely flat at this voltage, about 3.375. Now when this low part of the curve disappears off the history chart, of course the chart will recalibrate this axis and these two voltages will open out, and then we should start to see the stepping up in voltage as the battery is being charged. Sunny out there now, and the battery is up to 94%. And if we look at the history page, you can see that we got better resolution on the highest voltage cell and the lowest voltage cell. Now they are starting now to track up. They were flat for quite a long time. Now the balancing circuit will kick in. This here will go to status open once the highest voltage cell gets to about 3.4 volts. So it's currently 3.3, it's under 3.38. So I'll come back when the balancing starts. At 99% state of charge, although that is a Coulomb counted state of charge, it's not based on voltage. But here we have the balancer has now gone into an open state, so it is balancing the highest voltage cell. Let's take a look at that. And from what I can tell, this thing starts balancing once the cells get over about 3.4 volts, which is there, so they are over that. And also when there's a reasonable delta between, or voltage difference between the highest voltage cell and the lowest voltage cell, that's currently about this distance. So it's about 2/100ths of a volt. So yes, it is balancing now. We'll take a look in a minute at whether that affects the highest voltage cell, whether that flattens off a little bit. If you're wondering what that kink is there, I wound the current on the power supply outside down from 5 amps to 4 amps because I wasn't quite sure why the balancing hadn't started, but now it has. And it's not surprising we can't really see any effect on the highest voltage cell because I am charging at 4 amps now. There's the current curve there, and the balancing current is likely to be only 100 milliamps or possibly even less. So what's happening now is that the power supply, which I set to a voltage limit of 14.1 volts, has reached that voltage, and so it's winding the current back down. So it's down to 3.2 amps now, and it will continue to wind the current down to maintain that 14.1 volts. Of course, there is some volt drop in these cables as the current reduces, so the voltage on the battery will come up to that 14.1 volts. We can take a look at that on the app. So the power supply is now down to 2.7 amps. The balancing circuit is still operating. If I go to the graphs, you can see that because of the reduced current, the lowest voltage cell has actually flattened off, but the highest voltage cell is still increasing in voltage. So of course they're accelerating away from each other. We're not at the cutoff point where the highest voltage cell would have to get to 3.65 volts. We're at well below that. So the Coulomb counter is now saying 100% state of charge. It's actually gone to 99.51 amp hours. Balancing is still enabled. Let's look at the charts. Huge divergence now between the lowest and highest cells. It is about, well, at least I think a tenth of a volt. That's 100 millivolts. So you can see how massively the difference opens out when we get to almost a completely fully charged battery, whereas it was tiny back here. And just really now waiting for the highest voltage cell to exceed 3.65 volts, and then charging will be disabled because the charge MOSFETs will switch off. From what I can tell, it seems that the unit needs not much less than 500 milliamps coming in for the balancing circuit to be enabled, so I'm expecting that balancing to shut off fairly soon when the current drops a little bit lower. You can see that the highest voltage cell is very close to 3.65 volts. And then of course the input charge MOSFET will shut off and the battery simply won't charge anymore. There's now something like 200 millivolts between the lowest and highest cell, so they've really diverged. So the balance circuit has closed. That means it's disabled. So the top cell is now no longer being balanced, so it should drift up a bit more quickly. And then I'm expecting the charge switch to close, which kind of in switch terms means open really, but to be disabled. Let's look at the graphs. It's still not reached 3.65 volts, so it's going to sit there for a while. So the charge switch is still open, which means still enabled, so it's charging. The current is reported as 0, even though it's not actually 0. You can see that from this that it's still pushing about 300 milliamps into the battery, so the highest voltage cell will continue to rise in voltage. And you can see now that it is within a smidge of 3.65 volts, and when it reaches that, which it will because it's still on an upward trajectory, then the charge MOSFET switch will switch off. In other words, it'll become closed, and that's the end of charging. But I mean, essentially the battery is now fully charged. And now finally the charge switch has closed, which means that it's disabled, so it's no longer charging. The protection status has now opened, which means that the battery is protecting itself against further charge. There's no reported voltage and current, so the battery is now fully charged and protected against further charge. And now you can see that because the battery has gone into protected state, the cell voltages are falling away, both the highest voltage cell and the lowest voltage cell, and of course the average. I cheated a bit at the end. I just pushed the voltage limit on the power supply up to 14.2 volts from 14.1, which just put a little bit of extra nudge, tripped the 3.65 volt over voltage limit on the high cell, and put the battery into protected state. Okay, so that's it. That's all of the charging stuff. Now set up and ready for a full discharge. I've got a few extra light bulbs in my, I found some more H7, so I should hopefully be able to get about 20 amps this time. Let's start connecting light bulbs. Those 4. What's that? That's 6 amps. Okay, and let's get some H4s connected. Oh, yeah, we'll put that one in there. Put that one in there. And put that one in there. Right, what have we got? Yeah, they're all lit up. Current wise, oh yeah, 20 amps. That's kind of what I was hoping for. Okay, so the amp hour count is going down, and we'll wait until the battery disconnects. I just wanted to check the correlation between the ammeter on the Juntech discharge monitor, so that's saying 20.03, and the ammeter on the app, and that's saying minus 20, 20.08. Also, might as well check the voltage correlation, so 13.02 on the Juntech and 13.04 or 05 on the app. Okay, this has been running for about 5 hours. I think it's getting close to the point where it's going to shut off. We're wanting to see on this amp hour reading something below 20. That means we get above 100 amp hours from this battery, which of course it's rated at. So I will come back when it's just about to cut out. Right, we're down at just approaching 20 amp hours. So as soon as that gets down to 20 amp hours, then this battery has done its rated 100 amp hours. Now the voltage is still up at 11.2, so that's got a fair way to go down to 10 volts, which should be the point at which these light bulbs cut out. But there we are, we've just passed the going below 20 amp hours. I started at 120, so that is 100 amp hours. Let's see how much further it goes. Right, that's switched off, and the total amp hour rating is just approaching 101 amp hours, just shy of that. Now it didn't get down to 10 volts, it actually cut out at about 10.8, 10.9, something like that. But there we are, the capacity of that battery is in excess of 100 amp hours. So I've just hooked up a solar panel, and although the battery is charging, there's no information there because we have to get the lowest voltage cell up to 3 volts, which is actually up here, and it's not there yet. So until that cell gets up to 3 volts, we won't get anything, we won't get any data on the real-time page. And there we are, the parameters have come back on, 0% state of charge, but we now do have 1.5 amps going in from the solar panel, 12.27 volts and about 16 watts coming in from that panel because it's not very sunny. So that's the aolithium 12 volt 100 amp hour battery with Bluetooth, and the Bluetooth is surprisingly useful, more useful than I thought it was going to be. Even though the app is read-only, you can't change any parameters, it is extremely useful to be able to see things like voltage and current. And the battery yielded just shy of 101 amp hours, so in my book that's a pass. Cheerio.